Then we have the heap segment. This is where dynamic memory allocation happens, like when we use malloc or new. The heap grows upward into increasing memory addresses as more memory is allocated during runtime. Understanding these segments helps us see how memory is managed efficiently and securely during program execution, which ties directly into our overall theme of understanding process management in operating systems. Let's take a closer look at the stack segment. This area manages several critical aspects of program execution. It handles function calls, meaning it keeps track of where each function started and where to return after it finishes. It also stores local variables, which are temporary data specific to each function, and function parameters, the inputs passed into functions. Additionally, it holds return addresses, so the program knows where to go back after completing a function. An important point to remember is that the stack grows downward, toward lower memory addresses, which is a common pattern in many systems. Understanding how the stack operates is essential because it plays such a central role in managing program flow and data during execution. Now, moving on, let's briefly touch on the shared library, which is somewhat optional but very relevant in modern systems. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the process lifecycle in an operating system. When a process is first created, we call that the new state. This is when the process is in the process of being set up by the system. Once it's ready to run, it moves to the ready state, meaning it's prepared and just waiting for the CPU to get assigned to it. When the CPU starts executing the process, it enters the running state. This is the active phase where the process is actually being carried out. Sometimes, a process needs to wait for some external event, like completing an input-output operation. During this time, it enters the waiting or blocked state. It's temporarily paused until the event it's waiting for occurs. Finally, once the process has finished its task, it transitions to the terminated state, indicating that it has completed execution and is now finished. Understanding these states helps us see how an operating system manages multiple processes efficiently, switching between states as needed to optimize overall system performance. Now, let's take a closer look at process state transitions. These transitions happen based on system events and scheduling decisions, and understanding them is key to grasping how an operating system manages processes. First, when a process is created and resources are allocated, it moves from the new state to the ready state. This means it's prepared to run, but hasn't started execution yet. Next, when the scheduler selects this process to run, it transitions from ready to running. This is when the process actually begins execution on the CPU. While running, a process might need to wait for some external event, like input-output operations or other resources. In this case, it moves from running to blocked, essentially pausing until the required event or resource becomes available. Once the awaited event or resource is available, the process transitions back from blocked to ready, indicating it's now prepared to run again. Sometimes, the scheduler preempts a running process to give CPU time to another process, or if the process's time slice expires, the process moves from running back to ready. This ensures fair sharing of CPU resources among processes. Finally, when a process completes its execution or is terminated by the system, it transitions from running to terminated, marking the end of its life cycle. Understanding these state transitions helps us see the dynamic flow of processes within an operating system, highlighting how it manages multitasking efficiently. This slide doesn't contain enough information. That's why we're moving to the next slide. Now let's talk about the process control block, or PCB for short. So what exactly is a PCB? Well, it's a critical data structure that the operating system creates for every process. Think of it as the process's identity card. It holds all the essential information needed to manage and track that process effectively. This includes details like the process state, program counter, registers, memory management info, and I/O status. By keeping all this data organized in one place, the PCB allows the operating system to perform smooth context switching. That is, switching from one process to another without losing track of where each one is. In essence, the PCB is key to efficient process management, resource allocation, and ensuring that processes run seamlessly within the system. It's a fundamental building block that supports the overall stability and performance of the operating system. This slide doesn't contain enough information. That's why we're moving to the next slide. Now let's take a closer look at the key components of a PCB, or process control block, which is essentially the data structure that the operating system uses to manage processes. First, we have the process ID, or PID, which is simply a unique identifier assigned to each process. This helps the OS keep track of every process individually. Next is the process state, which tells us the current status of the process, whether it's new, ready to run, actively running, waiting for some event, or already terminated. Moving on, the program counter, or PC, holds the address of the next instruction the process needs to execute. It's like a bookmark that points the CPU to where it should be working next. Then, we have the CPU registers, which store the values of various CPU registers like accumulators, index registers, and stack pointers. These are crucial because they capture the execution context, allowing the process to resume smoothly after being interrupted. Another important component is the memory management info, which includes data such as page tables, segment tables, and base or limit registers. This information helps manage how memory is allocated and accessed for each process. Then, there's the CPU scheduling info, which contains details like priority levels, time slices or quanta, and scheduling queues. These parameters are vital for determining how the CPU allocates time to different processes. We also need to consider the I/O and file info, which details the I/O devices associated with the process and the list of files it currently holds open. This helps the OS manage resources effectively. Next, the accounting info tracks resource usage, including CPU time, execution duration, and memory consumption. This data is useful for billing, optimization, and monitoring system performance. Lastly, the inter-process communication and privileges section stores information related to IPC, such as signals and message flags, along with permission levels. This is especially important in multitasking environments where processes need to communicate and share resources securely. So, as you can see, each of these components plays a critical role in managing processes efficiently and ensuring smooth operation within the system. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at this diagram showing how the CPU switches from one process to another. As you can see, this switch is a crucial part of multitasking in operating systems. When a process needs to pause, either because it's waiting for I/O or because its time slice has expired, the CPU needs to switch to another process. This involves saving the current process's state, like its register values and program counter, so it can resume later without any issues. Then, the CPU loads the state of the next process to run, restoring its saved context. This switch ensures that multiple processes can share the CPU efficiently, creating the seamless experience we expect from modern computers. Understanding this process helps us appreciate the complexity behind what seems like a simple task, switching from one process to another. It's all about managing resources effectively